We have looked at the basics of quantum computing. We know about the four postulates. It is time to look at the applications. We will look at two applications this week. One is quantum teleportation and other is called Deutsch's algorithm. Both of this will in some sense show the power of the two key properties, superposition and entanglement. And we will see that quantum computing can do non-trivial tasks. When I say non-trivial task, I mean things which can be done, which cannot be done not by a classical computer. Before we dive into the applications, let's just see how the postulates affect the setting of quantum computing. This is just to remind you of what we have learned till now. The first postulate tells us that the simplest element of our system is a qubit. This qubit will have a state space of C square. Let's say it has two basis elements, 0 and 1. This corresponds to 0, 1 in classical setting. Then any state of this qubit can be written as alpha 0 plus beta 1, where this is a unit vector. The fact that we can have states where both alpha and beta are non-zero, this is called superposition, and we know that it is not simply that state is in 0 with probability alpha square and state is in 1 with probability beta square. That's just one consequence. That's not the state itself. We also notice that if we have two qubits, then we have to take the tensor product. The state space of two qubits will be C square tensored C square. If I want to talk about the basis, then one of the bases will correspond to the classical states, and then any state of two qubits would look like this. Again, the amplitudes should sum up to, the square of the amplitude should sum up to 1 because it has to be a unit vector. This was the basic way of representing states in a quantum system or in a quantum computer, I would say. This is our model. We also noticed that the gates which we can apply on these states have to be unitary. In general, I will have diagrams like this. That means there are 3 qubits, and then I'm applying some unitary here, and let's say a Hadamard gate on this, then a C0 operator on this, and so on, and the measurement is denoted by this. I will come to the measurement, but about these unitaries, we saw that we had single bit unitaries, poly X, poly Y, poly Z. We had Hadamard gate, which was taking 0 to state plus, 1 to state minus, and then we also noticed the C0 gate, which was in some sense a quantum XOR operator. If we have two states A and B, the action would be the first state, which is the control qubit, will remain the same, and the data qubit will change. In other words, flip if the control qubit is 1. This was the gate. These gates will occur again and again and again in our discussion of quantum computing. These are the basic gates. You should make sure that you understand these. Another postulate, the third postulate, talks about measurement. How do we find output from a quantum computer? We notice that if the state was alpha 0 plus beta 1, the simplest measurement was the measurement in the standard basis. This would be measure in the standard basis. What it would mean is that I have two projectors corresponding to the two basis states, two standard basis sets, 0, 0, P1, 1, and if I apply this measurement on this state, then I will get 0 with probability alpha square and 1 with probability beta square. By no means this is the only possible measurement. You can measure in different bases. You can apply a unitary and then make a basis transformation and then measure whatever you want to do. For example, you might want to see that I can define my two projectors like this also. Remember, plus state is 0 plus 1 by root 2, minus state is 0 minus 1 by root 2. You might want to figure out if my state remains the same as before, what is the probability of getting output as plus and what is the probability of getting output as minus. Notice that you have to convert the state into plus minus basis and then you will get these probabilities. It's not hard. I would request you to pause the video and do this exercise. See if you can figure out what will be the proper probabilities in terms of alpha and beta when you measure in this basis or with this projectors. That's the equivalent thing. We also saw that projector measurements are not the only measurements. There are generalized measurements, but most of the time we'll be dealing only with projector measurements. Great. We are now ready with the information we needed for our quantum system. Let's look at the application. The application is called quantum teleportation. My explanation of this is significantly inspired by the explanation given on this website, algassert.com. I would like to thank the author. He or she has explained it brilliantly how to understand quantum teleportation, and I would go into those details with you. Let's first ask, what is the problem? Let me say that the problem is inspired by people who would say that, oh, quantum computing is cheating in the sense that you are allowing one bit to store so much information. A bit is just 0, 1. A quantum bit is kind of hiding two amplitudes, alpha and beta. Both are complex numbers. You might want to say that there is so much information hidden in a quantum bit. And that's the reason why quantum computing is so powerful, because now you are saying that you have many copies of a bit and you're just calling them as a single qubit. And that's why with very few qubits, you can do a lot of information processing. To counter that, I will show you this protocol. What does it do? It transfers a quantum bit using classical communication between two quantum parties. Why do I need two quantum parties if they are only communicating classically? Let's just say that they have entanglement. So our task is to transfer a quantum bit. Let's say Alice and Bob are two parties. Alice has a state psi, alpha 0 plus beta 1. It could be any arbitrary state. Remember, Alice can't choose which state she wants it to be prepared in. Then it will be easy to transfer it to Bob. So Alice has a state, an arbitrary state, and she wants to transfer it to Bob. The problem is, one, they only have a classical communication channel. They can't transfer quantum bits. Another thing is that since Alice and Bob both have the capacity to store quantum bits, we can assume they share entanglement a priori. That would mean that I have two qubits, 0, 0 plus 1, 1 by root 2. One of the qubit is with Alice, other is with Bob. There is no way to write the state of the Alice's part of the qubits and Bob's part of the qubit separately. They have two qubits. They probably had met long time back when they had no clue about what psi was. They just shared this fixed state. Notice that it is not cheating that we already have an entangled state. The entangled state does not depend on psi. It is a fixed state which they might have shared before the protocol started. Now they are sitting far away. They have no way to figure out what psi will be given to Alice. But this protocol will show that whatever psi be, it can be transferred between Alice and Bob. In terms of practical applicability, you can also think in future we might be able to build quantum computers which are sitting far away. One is in US, one is in India, let's say. So the qubits can be transferred locally inside a small room in India. Qubits can be transferred inside the room in a US lab or something. But obviously, it's much harder to have a network which transfers quantum bits. Though we have phones and methods by which we can transfer classical information. Even then, we can transfer quantum messages. It will require, obviously, classical communication, the channel which is given to us, phone, fax, internet, whatever you want to say. And secondly, US and India should have shared pair of it. That shared pair could have been exchanged long time back. It does not depend on the information to be transferred. In this sense, this protocol seems magical. One quantum bit gets transferred using 2 bits of classical communication. This is the description of the problem. And before we go into the quantum protocol, let's see how you would do something like that on a classical computer. This protocol of transferring a quantum bit looks very much like a swap. You have 2 bits A and B. Let's say A is with Alice and B is with Bob. You want to design a circuit so that they get swapped, then Alice will have B and Bob will have A. In your first course on computing, you must have definitely solved this problem. This is very easy. You would have a temporary register, and what you would do is that you would put the value of A in temp, then you would assign A to B, and then you will assign B to temp. This is the standard way of swapping 2 bits. This seems very easy in the classical setting. One problem is no temp in a quantum computer. You know that we can't copy states. This is not possible in quantum computing. Can we swap bits classically while not making a copy? Another trick will allow this. What do we want to do? We want to swap without making copies. Because we can't make copies in quantum computer, then the task is to swap classically, and in that case we cannot use the temporary variable. This is a trick which works for 2 bits. Let's say I have A and B bit, then I would do A is equal to A plus B, B is equal to A plus B, and then A is equal to A plus B. You can convince yourself that in this case, after this, A and B will be swapped. If this is not clear to you, pause the video and just check that after these operations, A and B are swapped. This XOR operation allows us to swap without using the temporary variable. And we know the quantum equivalent of XOR. This is going to be a very simple circuit to swap 2 quantum bits. I'm just doing the same thing, but I'm replacing XOR by C0 because I know that quantum equivalent of XOR is the C0 operator. And you can convince yourself that this will swap 2 qubits. From the classical case, it is clear that this circuit will swap the basis states, because on basis states C0 is same as XOR. So on basis states, these two are saying the exact same thing. And then by linearity, you will get that for any 2 general quantum states, swap will work. This circuit will work for any 2 basis states. You can check and convince yourself. Nice. But obviously, this is not good for us. In the quantum teleportation, we don't have ability to apply the gates simultaneously on the two qubits x and y, because x and y are far away. One is in US, one is in India. We can't apply a single gate, a C0 gate, on these two qubits. Our task would be to replace these C0s using classical communication and entanglement. This will be done